All right, today we're going to have a look at another topic in chapter 4, quantum mechanics and bonding hybridization. Okay, first let's have a look at introduction. Example, benzene. Benzene is commonly known as a nonpolar liquid, known and used by pharmacists and perfumers in various forms since the 15th century. English scientist Michael Faraday was the first to isolate benzene and determine its molecular formula, C6H6. For decades, the unusual formula of benzene stumped chemists because they were unable to determine the structure of a molecule that has an equal number of carbon and hydrogen atoms. Finally, in 1865, 40 years after Faraday's discovery, the German chemist Friedrich Kekule proposed a three-dimensional structure for benzene, which is shown here in figure 1. Notice how in this structure, each carbon atom bonds to one hydrogen atom. It took another 65 years before this ring structure was confirmed by X-ray crystallography. This technology also revealed that all of the carbon-carbon bonds are equal in length, shorter than single bonds but longer than double bonds. The understanding of benzene structure was so important at the time that 25 years after Kekule's first paper, the German Chemical Society honored him with an elaborate celebration. There, Kekule explained how he recognized the cyclic structure of benzene from a daydream in which he imagined a snake seizing its own tail. Look at the two different structures for benzene in figure 1. What difference do you notice between them? The simplified Lewis structure in figure 1a suggests that there are two types of carbon-carbon bonds, 3 single bonds and 3 double bonds. In such a structure, electrons making up the double bonds are always localized between the same two carbon atoms. A model of the three-dimensional charge distribution in benzene would be expected to show the carbon-carbon double bonds having a higher electron density than the carbon-carbon single bond. Yet, the computer-generated model in figure 1b shows only that electron density decreases uniformly as we move away from the center of the molecule. This model suggests that there are no differences in the length of any of the carbon-carbon bonds, and that the electrons are concentrated in the center of the benzene ring. So how have scientists explained these observations of the structure of benzene? One explanation is that the electrons in the carbon-carbon double bonds are not always localized between the same two carbon atoms. This idea is based on the concepts of quantum mechanics. We learned in chapter 3 that the location of electrons is defined by probability distributions, regions in space where there is the greatest likelihood of finding an electron, right? The Lewis structure of a molecule provides a simplified view of bond formation and allows us to determine the number of bonding and lone electron pairs. We can then predict molecular geometry using the VSEPR theory. But neither Lewis structure nor VSEPR theory describes how bonds are actually formed and how orbitals interact. So in this lesson, we'll learn more about molecular orbitals and how they are involved in bond formation. In the previous chapter 3, we learned how quantum numbers are used to describe the locations of electrons in an atom, right? Electron clouds can be constructed for a particular atom to represent areas that have a high probability of containing an electron. The complex Schrödinger wave functions and probability densities can be used to describe bonding and electrons. However, calculating the electron clouds surrounding a single atom much less in a bound, is difficult. Even though modern computers have expanded the scope of quantum mechanics calculations to include relatively large molecules, the computer power and time needed to calculate electron clouds increase dramatically as the complexity of the molecule increases. So it's very difficult to calculate quantitatively the distribution of electrons in the bounds of unusual molecules. A simpler approach to describing the location of electrons in bounds is to start with an atom and its valence orbitals, and to form covalent bonds in these atoms through the valence orbitals. This method is called the valence bond theory. According to valence bond theory, a covalent bond forms when two atomic orbitals, each with an unpaired electron, overlap. When the covalent bond forms, the lowest energy state is obtained when predicting electrons are of opposite spin. The simplest example of the valence bond theory is the bonding of two hydrogen atoms. So we're going to have a look at the simplest cases first. The electrons in each of the hydrogen atoms reside in the 1s orbital, which is shown here in figure 2. When the 2s orbital overlap, a covalent bond forms. In this bond, electrons in the bounded 1s orbital have opposite spins, which is shown here in figure 3, similar to a filled atomic orbital. So when the hydrogen molecule forms, as shown here in figure 3, each 1s orbital, which is shown here in figure 3a, overlaps to form a covalent bond, and in the hydrogen molecules, electrons have opposite spins with a lower energy state than the separate hydrogen atoms, which is shown here in figure 3c. The example of two hydrogen atoms forming a covalent bond involves electrons from the 1s orbital. Yet any unfilled orbital can overlap with another unfilled orbital. The diatomic molecule hydrogen chloride, HCl, also forms covalent bonds. The hydrogen atom contributes one electron from its 1s orbital to form the bond. The valence orbital diagram of a chlorine atom is shown here on the top left. So in the chlorine atom, the 3s orbital and two of the 3p orbitals are full with two electrons of opposite spin, right? However, one of the three orbitals here contains one unpaired electron. The 1s orbital from the hydrogen atom can overlap with this 3p orbital in the chlorine atom to form a covalent bond. And this concept is shown here in figure 4. So as you can see here, the p orbital in the chlorine atom has two lobes. When the bond forms, one lobe of the chlorine atom overlaps with 1s orbital from the hydrogen atom. So the valence bond theory involves taking existing atomic orbitals and overlapping them to produce new molecular orbitals for the bounding electrons. These new molecular orbitals concentrate electron density between the bounded atoms, as the VSEPR theory postulates. The VSEPR theory assumes that the majority of the electron density for bounded pairs of electrons is in the vicinity of the bound. The valence bound theory helps explain why this assumption is justified. Okay, so far we have considered only bounding in diatomic molecules, right? The valence bound theory can also describe bounding in polyatomic molecules. So now we'll consider a molecule of ammonia, which consists of one nitrogen atom and three hydrogen atoms arranged in a trigonal pyramidal structure. The valence electron diagram of the nitrogen atom has three unpaired electrons in the p orbital, which is shown here on top left. And each of the three hydrogen atoms contributes one electron from its 1s orbital, right? From the previous example, we would expect the three unpaired electrons from the 2p orbitals of the nitrogen atom to overlap with the 1s orbital of each hydrogen atom, forming three covalent bonds that have a lower energy state than the individual atoms. And this concept is shown here in figure 5 on the bottom. And the final structure in figure 5 suggests that the bound angles in ammonia are 90 degrees. However, we know from the VSEPR theory that the geometry of ammonia is a trigonal pyramidal structure with bound angles of approximately 107 degrees. To account for this observed bound angle, valence bound theory must be expanded to include the concept of orbital hybridization. Okay, so next let's have a look at the concept of hybrid orbitals. So suppose we were to use valence bound theory to describe the bounding in the molecule of methane, CH4. Each hydrogen atom contributes one 1s electron. When we place the 4 valence electrons for carbon, one of the 2 electrons in the 2s orbital must go into the empty 2p orbital, right? And this concept is shown here on top right. Since the s and p orbitals have different shapes, they should form two different types of chemical bonds with the 4 hydrogen atoms. One bound type would result from the 2 overlapping s orbitals, and the other would result from overlapping an s and p orbital. However, the CH bonds in methane are all of equal length and are arranged symmetrically in a tetrahedral geometry. This is one of the problems with the valence bound theory. So how does this account for the 4 equivalent chemical bonds in methane? The chemical bonds in molecules such as methane can be explained by the concept of hybrid orbitals. Hybrid orbitals form by combining orbitals with different shapes. For the carbon atom, we start with 1s orbital and 3p orbitals, and finish with 4 hybrid sp3 orbitals. The process of forming hybrid orbitals is called hybridization. This concept is shown here in figure 6, which illustrates how sp3 hybrid orbitals form. Okay, so each of the hybrid sp3 orbitals is identical now to each other, right? Since each hybrid orbital contains an unpaired electron, these sp3 orbitals can overlap with the 1s orbital of the hydrogen atom to form the 4 equal covalent bonds in the methane molecule. The sp3 hybrid orbitals have a large lobe and a small lobe pointing in opposite directions, which is shown here in figure 7. The large lobes of the 4 sp3 orbitals have the tetrahedral arrangement predicted for the bounding electron pairs in the VSEPR description of the methane molecule. This is why this creates 4 hybrid orbitals with similar properties and results in equivalent chemical bonds with each hydrogen atom. There are many other examples where hybridization is needed to account for the observed properties of the chemical bonds. Another example is the beryllium hydride molecule, BeHl2. Each hydrogen atom contributes a single 1s electron to each chemical bond, right? The valence electron diagram for a beryllium atom is shown here on the top. Notice that there are no half-empty orbitals available for bonding, right? For a chemical bond to form, the s orbital and one of the p orbitals hybridize after a 2s electron is promoted to a 2p orbital, leaving 2 empty 2p orbitals. The result is the formation of 2 equivalent hybrid sp orbitals. The sp orbitals have a linear arrangement, so a beryllium molecule has a linear structure, which is shown here in figure 8. Okay, now let's consider the boron molecule, BH3. Using the VSEPR theory, we can predict that this molecule has a trigonal-planar structure and that each hydrogen atom contributes 1 s electron to each chemical bond, right? The valence electron diagram for the boron atom is shown here on the top. So an electron is promoted from the 2s orbital to a vacant 2p orbital. There are now 3 unpaired electrons, 1 in the s orbital and 2 in the 2 different p orbitals. So these orbitals combine again to form the hybrid sp2 orbitals. The sp2 orbitals have a trigonal-planar arrangement, which is shown here in figure 9. And the hybridized sp2 orbital results in 3 equivalent chemical bonds to the hydrogen atoms. Alright, if you know the orbital hybridization theory, now let's look back at the molecule of ammonia. So now we know there must exist a hybrid atomic orbitals in the nitrogen atom, since the angles of nitrogen-hydrogen bonds, which is 107.3 degrees, are closer to 109.5 degrees, right? In which bounded pairs occupying 3 of the 4 sp3 orbitals and lone pair being the remaining sp3, rather than the cases where we have a 90 degrees for bounded pairs occupying 3 of the 3p orbitals and lone pair being on the s orbital, right? Therefore, the sp3 bonding picture is also used to describe the bonding in amines, including ammonia, the simplest amine. Just like the carbon atom in methane, the central nitrogen in ammonia is sp3 hybridized. With nitrogen, however, there are 5 rather than 4 valence electrons to account for, meaning that 3 of the 4 hybrid orbitals are half-filled and available for bonding, while the 4th one is already fully occupied by a non-bonding pair of electrons. And this concept is illustrated in the picture in the middle. Okay, so here, table 1 shows common hybrid orbitals and the resulting molecular structures that form from these orbitals. Alright, next let's have a look at the cases where we have double or triple covalent bonds. The valence bond theory creates a second dilemma. How do we describe the chemical bonding in molecules with multiple bonds? In the molecules we have examined so far, bonding occurs between unpaired electrons from s orbitals, for example, hydrogen to hydrogen bond, p orbitals, for example, hydrogen to chlorine bond, and the sp, sp2, and sp3 hybrid orbitals, for example, beryllium hydride, borane, and methane, respectively. These orbitals directly overlap with each other. When one end of the orbital meets the other orbital, the lobes of each orbital point towards each other. This direct overlap results in formation of a sigma bond, which is a bond that is formed when s orbitals, p orbitals, or hybrid orbitals overlap. And this concept is shown here in figure 10. However, sigma bonds do not explain how multiple bonds form. Therefore, a different type of bond must exist in molecules with double and triple bonds. In a multiple bond, orbitals that are parallel to each other overlap, which results in the formation of pi bonds. The formation of pi bonds between two p orbitals is illustrated here in figure 11. So as you can see here, two p orbitals form bonds when the size of the orbitals overlap. The result is that the electron density is above and below the bond axis. So to investigate the formation of pi bonds, consider the double bonds of ethene, C2H4, from the Lewis structure of ethene, which is shown here in figure 12a. We can see that each carbon atom forms bonds with three other atoms. These bonds are sigma bonds that directly overlap with each other. The carbon atom undergoes partial hybridization to form these three sp2 orbitals. The remaining p orbital is left with one electron in it, which is shown here in figure 12b. And in ethene, both carbon atoms are partially hybridized in this way. The carbon atoms can each form three sigma bonds using the sp2 orbitals. One sigma bond forms with the second carbon atom, and two sigma bonds form with hydrogen atoms, which is illustrated in figure 13a here. This arrangement leaves each carbon atom with one additional unpaired electron in the p orbital. These unpaired electrons form the pi bond. The pi bond forms in the region above and below the sigma bonds, which is shown here in figure 13b. A double bond always consists of one sigma bond and one pi bond. In the sigma bond between the carbon atoms in ethene, the electron pair resides in the space between the atoms. In the pi bond between the carbon atoms, the electron pair occupies the space above and below the sigma bond. The electrons in the pi bond have opposite spins, just as in sigma bonds. Since there is an additional pair of electrons between atoms in the pi bond, a double bond is shorter in length than a single bond. In addition, a double bond is stronger and requires more energy to break than a single bond. And pi bonds are also present in triple bonds. To illustrate triple bonds, consider the molecule ethine, C2H2, commonly known as acetylene. The Lewis structure for this molecule is shown here on the bottom right. Since ethine is a linear molecule, neither the sp3 nor the sp2 hybrid orbitals will describe the bonding in this molecule. As for double bonds, we have seen that all of the orbitals in the carbon atom do not necessarily form sp3 hybrid orbitals. A partial hybridization is possible, in which two sp hybrid orbitals form, and two remaining p orbitals each hold a single electron. In ethine, both carbon atoms are partially hybridized in this manner, which is shown here in figure 14. The carbon atoms can each form two sigma bonds using these sp orbitals. One sigma bond forms with a second carbon atom, and one sigma bond forms with a hydrogen atom, which is shown here in figure 15a. Each carbon atom is left with two additional unpaired electrons, right? Each in a p orbital, and this concept is shown here in figure 15b. These unpaired electrons form pi bonds with the second carbon atom. One pi bond forms in the region above and below the sigma bonds. The second pi bond forms at a 90-degree angle from the first pi bond. Thus, a triple bond consists of one sigma bond and two pi bonds, which is illustrated in figure 15c. Okay, so at last, let's have a look at the bounding orbitals in benzene. Sigma bonds form between the carbon and hydrogen atoms and between the carbon atoms. Pi bonds form between the carbon atoms. As in ethene, the pi bonds occupy the space above and below the sigma bonds. However, in benzene there are 6 electrons in the pi bonds. These electrons are distributed in a ring shape above or below the sigma bonds, anywhere within the ring. So these figures are the representations of pi bonding in benzene. Okay, so this wraps up today's lesson. I hope you all learned something today, and I'll see you next time. Bye.